Yes, yeah.
Cool. Yeah, so so for today's tutorial, we are going to, so quickly in this slide, we're going to go through the agenda and also the goal of the tutorial and mention target audience and some technical setup. So if you have not gone through the technical setup, we will give you a quick intro, and then hopefully you can follow the guide, more detailed guide in the tutorial website to finish the setup procedure. So as the agenda, so overall we have prepared 6 videos to give you introduction about different parts. We will dive into each video shortly. And then for the goal of the tutorial, we want to first demonstrate a collection of forecasting approaches to solve forecasting problems in retail. And hopefully these approaches can be easily extended to other domains like finance and etc. And we also would like to introduce a new repository focusing on best practice in forecasting domain, along with a library of forecasting utility. We hope people are interested in this repo can also try to contribute, because this is not mean the repo is not means like end solution for all the industry. We are kind of planting a seed, and hopefully people can contribute their models to solve forecasting problem in different industries. And then also yeah, we hope that you have some background about forecasting, but we don't expect you expert in this area, because we want eventually you can get some of the helpful resources from our repo. And this is the technical setup, and we will actually introduce all these details in the video as well, so I'm not going to talk about too much. So basically you just want to you just need to run through either the Linux setup script or the Windows setup script, then you are good to go to run the examples in our forecasting repo. And yeah, and then we in this slide we also introduce like the content of each video. So for the second video, we will introduce like a basic some basic concept about time series forecasting, and also give an overview of the forecasting repo. And yeah, so this is like basic concept of forecasting, and you should know what is forecasting horizon, and what is the temporal frequency, and so on, after you watch the second video. And the data we use. Yeah.
Chenhui, sorry to interrupt. Yeah, so all of this is going to be covered in videos, so I think it's probably okay to just play them.
Okay, but yeah, that's a great point. So yeah, so in this regard, I'm not going to like talk about all the slides, but yeah, briefly, like all the slides are here, and we will probably share that share the slide deck after the tutorial. And up next, I'm going to just play the first video, which will give a overall introduction about the tutorial and how to set up the environment for you to run the example.
Welcome to the KDD hands-on tutorial of building forecasting solutions using open source and Azure machine learning. I am Chenhui, data scientist from Microsoft. This tutorial will be presented by my colleague Vanja Paunic, who is also a data scientist at Microsoft, and myself. For your convenience, we have divided the content of the tutorial into several sections and prepared a video for each section to walk you through the steps. In this video, I will introduce the agenda, tutorial goals, target audience, and setup instructions. This is the agenda of the tutorial. We start from the tutorial introduction, then we will go through the basics of time series forecasting and the content of the repository. Next, we will introduce statistical time series forecasting using AutoArima. After that, we will walk through how to build light GBM model and achieve accurate forecasts by hyperparameter tuning. Finally, we will further introduce a deep learning model that uses dilated CNN. The goals of this tutorial are twofold. First, we would like to demonstrate different forecasting approaches to solve forecasting problems in retail. Second, we would like to introduce a new repository focusing on best practices in forecasting domain, along with a library of forecasting utilities. The target audience are data scientists and machine learning engineers that are interested in building forecasting solutions, as our content is source-owning and targets custom machine learning modeling. We hope that you have basic knowledge of Python and time series forecasting. In addition, it would be great if you are comfortable with basic concept of machine learning and have some experience of building machine learning models. To guide you through the tutorial, we have created a tutorial website that includes detailed information about the tutorial. You can follow the setup instructions in the website to set up the environment for running the examples in the repository. In a nutshell, the main thing you need to do is to run a setup script after cloning our repository. We have setup scripts that can run on Linux and Windows systems. You can pick the setup script based on your operation system. Before we look at the list of setup steps, please make sure that you have conda installed and run the setup script from the root directory of the repository. Next, I will go to the tutorial website and briefly walk through the setup steps. So this is the tutorial website, which includes the tutorial overview and the outline, as well as a table of content. The most important part that you need to know is the Get Started in Python section, because you will need to follow the steps here to set up the environment. As you can see, the first step is to install Anaconda or Miniconda with Python 3. Then you need to clone the forecasting repo and switch to the root directory of the repo. The next step is to run the setup script, which will install the dependencies for you. This step may take about 5 to 10 minutes, so please be patient. There will be a conda environment named forecasting env after the script finishes. After that, please activate the conda environment and start Jupyter to test out the example notebooks. If you have any issues with the above setup or want to find more detailed instructions on how to set up your environment and run examples provided in the repository, please further refer to the setup guide here. So in this setup guide, we have included more detailed description about every single step that you need to take for setting up the environment. So please feel free to check it out in case you need find further information about the setup steps. So that's all for the tutorial introduction. In the next video, Vanja will introduce the basics of time series forecasting and provide an overview of our repo. Thank you.
All right. So this is a very quick introduction about. This is a quick introduction about our hands-on tutorial. So feel free to let me know if you have any questions. I'll try to go back here. Yeah. All right. So if you are good with the setup of the environment, we can go to the next video. Vanja, do you want to take over?
Sure, yeah. And if you have questions at any point during the presentations, just feel free to post them in the chat, and we'll address them during the breaks between the videos. All right. So let's go on to the next video. Hello, everyone. My name is Vanja Paunic, and I'm a data scientist at Microsoft, and I will be walking you through the second video of this tutorial. So in the second video, we'll cover three main topics. Introduction to time series forecasting. We'll just briefly cover what it is so that everyone's on the same page. We'll cover an overview of the public forecasting best practices repository. So this is the repository that we've based this tutorial off of. So all of the material that you'll be running in this tutorial is in this repository. And finally, we'll go over the notebook that allows you to explore the data set used across the examples in the tutorial. So let's first cover what time series forecasting is. So time series are observations taken sequentially in time, and time series forecasting is trying to predict the future based on the past or historical data. So typically in time series, we have a data set such as this one on the right, where we have two columns. One is date, or more generally, a timestamp. And on the right, we have an observation, or the quantity, or the value that we're trying, that we're recorded in the past and that we're trying to forecast in the future. So typically in a time series is generally contains these two columns ultimately, or these two values, the timestamp and the observation that we've taken in the past and want to forecast in the future. But oftentimes in time series forecasting solutions, we are actually trying to also include other relevant information that may improve our forecast. So for example, in retail scenarios, we may want to include weather as let's say during the summer, people are buying products that may, help them survive the summer, such as AC or, cooler juices or something like that. So the sales of those products will be impacted by the weather. So oftentimes in forecasting, we're actually using external features to help us improve the forecasts. So questions to ask before building a forecasting model. Is the value that we want to know in the future something that can be forecast? So basically how well we understand the factors that contribute to it, and how well do we not only understand the factors, but also are we available and are we able to gather the data that can help us derive those factors that contribute to the forecast? Second question we want to ask is how far in the future we want to forecast. So this is often taken from a business need of the solution that we're building. So basically, how far in the future do we need to know the forecast? This future is typically referred to as a horizon, and oftentimes, more generally, it's easier to forecast on the short horizon than longer in the future, or your forecasts are more accurate in the nearer term than the longer term. The third question is also at what temporal frequency are forecasts required? So basically, do we need to forecast an hourly values or daily values, or do we need to produce weekly forecasts, monthly forecasts, and so on? And finally, what technique or model should we use for forecasting? There's a variety of techniques to use in forecasting, and in this tutorial, we'll cover some of them. So in the tutorial, we'll be using a retail sales forecasting scenario. So we'll be using an orange juice dataset across all of our examples. This dataset is taken from our package base M and is a part of the Dominic's dataset, larger Dominic's dataset. We'll go into more details about this data set in the notebook that we'll cover. But just on a high level, this data set contains weekly sales of orange juice at a number of stores, at 83 stores. It contains a number of features along with the observations or the actual sales taken at these stores. And in addition to this, it contains demographic information from these stores. Let's go now to the repository from which we'll be taking these examples. So this is the Forecasting Best Practices repository. It provides examples and best practice guidelines for building forecasting solutions. And the goal of this repository is to build a comprehensive set of tools and examples that leverage recent advances in forecasting algorithms to build solutions and operationalize them. So the examples and best practices are provided as Python Jupyter notebooks and are markdown files. And finally, we also have a library of utility functions and in both languages, Python and R. This tutorial is focused on Python solely, but we'll sort of show you where the R files are as well. So feel free to play with those as well. So let's navigate to the repository now. So when you click on the link presented in slides, it will take you to this page. This is a GitHub page created specifically for this tutorial. However, it's forked off of the original repository here on the GitHub. But let's cover just sort of this GitHub page first before we jump into the GitHub source files here. So it provides just a brief overview of the tutorial outline. Currently, we're on this section of the video for the video 2. If you scroll down, you'll see the repository content.
Excuse me, Vanja.
So this is a table that sort of presents you with. Yes.
So there's a question asking that could you make this slides full screen because they are a little blurry for
Okay.
screen.
Let me see. Is this better at all? So this is playing a recorded video, and so I'm not sure how much I can zoom it in, but does this look a bit better?
It still looks blurred to me.
Okay. Can you read at all, or is it completely incomprehensible?
I can only read the head title, the repository content, and no other things.
Okay. Is it appearing like that to the rest of the audience as well?
Yeah, I think to many of them, they experience the similar thing to me.
I think it's slightly better when you enter the full screen mode on your right side.
I see. I see. This is not it. Okay, let me see. So this is the only option I see for zooming.
Do you have a different screen? I mean, physical screen, so you can share different.
I don't, unfortunately. Was it more visible from Chenhui's computer when he was presenting? Because we can switch to his computer as well. We can try that.
I think so. Yeah, we can try that.
Mm-hmm. Chenhui, can you hear?
Yes. So do you want me to play this video from
Yes.
the point that, from the current point?
Yeah. So it's about 6 minutes here,
6 minutes.
6:17.
Okay.
Yeah. Thanks. Yeah, I'll stop sharing.
Okay. Then I need to go to. So, sorry, let me just quickly share my screen.
Yeah, I also just want to note to everyone that all of these videos are available on the Whova app. So if you want to kind of revisit some of them after the tutorial, you would you would be able to kind of see them more clearly there.
Yeah, that's a great point. So people can feel free to download the video file from Hua app. Okay, so I'm going to share the screen now to see whether it will be better in terms of the resolution. So,
a brief overview of the tutorial outline. Currently, we're on this section of the video for the video 2. If you scroll down, you'll see the repository content. So this is a table that sort of presents you with some of the methods that are implemented here in the repository and that we'll go over in this tutorial. So we'll cover a traditional ARIMA or statistical approach to forecasting using AutoARIMA, which is autoregressive integrated moving average model that is automatically selected. We'll cover linear regression model trained on lagged features of the target variable and external features. We will go over the gradient boosting decision tree implemented with LightJBM package. And finally, we'll go over the deep learning approach to forecasting, or the dilated convolutional neural network that captures long-range temporal flow with dilated causal connections. Here you'll see several approaches that are implemented in R, more specifically mean forecast, which is a simple forecasting method based on historical mean, ARIMA, also using an AutoARIMA approach, ETS, or exponential smoothing algorithm with additive errors, and PROFIT, or automated forecasting procedure based on the additive model with nonlinear trends using the PROFIT package from Facebook. So these are the implemented in R, and if you follow these links, it'll take you to the corresponding HTML files produced from the R Markdown notebooks. Finally, we also have several notebooks that showcase closer integration with Azure Machine Learning Service. So Azure Machine Learning Service has several sort of components that allow you to easily train and manage the models on Azure. So Azure AutoML here specifically refers to the service that automates model selection. So there's a notebook here demonstrating model development process and identifying the best machine learning pipeline using Azure AutoML. In addition, we have Azure ML service for tuning hyperparameters of machine learning models in parallel on cloud using a service called Hyperdrive. And we have an example notebook that demonstrates how to deploy a model as a web service on Azure container instances. So hopefully at this point you've gone through the setup. So you've set up your environment following the getting started in Python instructions. We also have getting started in R instructions here, and some references here that we've kind of used for the development of the repository. But if we now go to the repository here, you'll see basically all the source files that we're using in the tutorial. Examples are where the notebooks that we're going over live. fclib here refers to the library of forecasting utilities written in Python. And rutils here refers to the library of forecasting utilities written in R. So if we navigate to examples, we will see that the grocery sales scenario here is the only scenario we currently have implemented in the repository, and that it's using Dominic's orange juice dataset. We have 2 implementations. So if we navigate to grocery sales here, you'll see directories for R and Python. If we navigate to Python, we will see a number of notebooks here covering the methods and Azure Machine Learning integration that I've told you about before. So as a part of this video too, as a part of the upcoming videos, we'll cover pretty much all of these notebooks. But as a part of the video 2, we'll simply peek into the OJ Data Exploration notebook here to have a sneak peek into the data set that we'll be using across all of the examples. Pretty much the rest of the notebooks here, other than these data preparation ones, implement one or another forecasting method or Azure Machine Learning here integration. So let's look into the OJ Data Exploration Notebook. So as I mentioned, hopefully at this point you've gone through the setup and you've installed a Conda environment called Forecasting Env and registered it with the Jupyter server as a kernel. So then when you open this notebook, you can select Forecasting Env as the kernel of your preference. So if you go to kernel, change kernel, this should be one of the environments you can select from. This will ensure that all of the packages required for running this notebook will be installed and available to you at the time that you want to execute this notebook. Okay, so the orange juice dataset contains two tables. One table is called here yx.csv, and another table storedemo.csv. So yx.csv contains weekly sales of refrigerated orange juice at 83 stores. It contains 139 rows and 19 columns. It includes weekly sales and prices of 11 orange juice brands, as well as information about profit, deal, advertisement for each brand, and so on. Note that the quantity that the sales or the quantity that we're trying to forecast is named log move, which corresponds to the natural logarithm of the number of units sold. So to get the number of units sold, after we do the forecast, we will need to apply an exponential transform to this column. Next, we also have a file called storedemo.csv, which is the demographic information on those stores. So this table has 83 rows and 13 columns. For every store, the table describes demographic information of its consumers, distance to the nearest warehouse store, average distance to the nearest 5 supermarkets, and so on. Note that this is only a subset of the full Dominic's dataset. So the full Dominic's dataset includes basically a larger time span and more stores for these orange juice brands. So if you would like to use the entire Dominic's dataset, you would have to go to the original source of the data, which is provided here. Currently, we provide utilities only to load the data from the base M package in R. So let's go first load the utilities that are required for running the notebook. We will also download the dataset by executing this script, this cell here. And finally, once we've downloaded the dataset, note that for this we're using a download OJ data utility provided as a part of the fclib library, here as a part of the forecasting repository. Okay, so now to look into these two files, let's first load them into data frames called sales and store demo. So if you look at the first 5 rows of sales, we basically get the past sales data. So our unique identifiers are store, brand, and the week. So basically we will be doing forecasts in all examples for each store and for each brand and for a number of upcoming weeks. So our week, as mentioned in the introduction, start at 40. We will be doing forecast for 3 weeks, I believe, in the future, but we'll go over that notebook in the upcoming video. So the quantity that we want to forecast is given here as log move, which is the sales, the natural logarithm of sales. Finally, we have some information about the prices. These are actually the prices for that given week for all 11 brands, as the sales of any particular brand may be impacted by the price of a competing brand of the same product. If you look at the store demo information, we'll basically get information, some demographic information for each store. So these are some external features that we may want to use in our in building a machine learning forecasting solution, let's say, that may improve our forecast. So there is information, for example, on income, let's say an average income for that across customers for that given store, ethnic background, education level, age, and so on. And finally, these variables towards the end refer to the information about the location of that store. So if we execute this cell here, it will give us some information about how many stores, brands, and time series we have. So we have 83 stores, 11 brands, and in total of 913 series. So for in the upcoming videos that we'll show, we'll basically be training a model for each of these 913 time series. If you look at the length distribution of the time series, you'll see that we have a 913 series. However, the average length of these series differ, which typically means that the time series that we've collected are incomplete. So what we're doing here in this cell is we're simply filling the missing values in the time series. There are different ways to do this. We are currently basically inferring the missing values as 0. But some common approaches are to backfill or forward fill. That is to take the previous existing value or the future, the next existing value as the current value, or to take some sort of average of the values in the neighborhood. So let's visualize some time series. So we are here in particular just selecting a single time series. So we're selecting a sample store 2 and sample brand 1. And we are visualizing this time series to see if there's any trends or patterns we can just visually see. It's common that in retail applications, you can, unless you're looking at a very high aggregate level across a category of products or across a store or across seasons, you can see some patterns, but oftentimes when you look at the SKU level, single product, the time series can tend to be kind of erratic and do not show much pattern, which is kind of in case of this time series. Let's look at the time series for all brands for a sample store of 2. So this is showing time series for brand 1, brand 2, and so on until brand 11. And we can see that some brands sell better than the others. The time series is kind of erratic. These brands that don't sell as much have a bit of a smoother patterns here. But it's kind of hard to infer any higher level patterns by just looking at the time series. So in the next set of cells here, we're looking at impact of other features that we have in the data set on the time series. So in this particular case, we're looking at the impact of demographics, brand, and store. We've observed, so if you run this cell, you'll look at the correlation of these external variables with the sales. We've observed that once we include basically the store information and brand variables as the grain or the key variables across which we're training the machine learning models, the contribution of the demographic variables seem to be limited. And we're looking at some other correlations here and plots. Feel free to play with these and kind of see how they change based on the values that you change. Also looking at seasonality and autocorrelation here, there seems to be limited seasonality in this data, as orange juice tends to be sold year-round pretty consistently. And finally, one thing I want to point out here in this notebook is impact of price. We will be using price as one of the features, external features, for our time series forecasting in a number of notebooks, simply because price does tend to impact sales of products. Typically what we see, if you decrease the price of a product, the sales increase, and other way around, if you increase the price, the sales of that product tend to decrease. And so as a general, we see that trend shown here on the plots. So this is basically the notebook to allow you to kind of look through the data set that's available to us in this repository, in this tutorial, feel free to basically change any values and things you want to plot and show here in these notebooks, and use this notebook to explore the data set, the orange juice data set. Thank you for listening to video 2. In the next video, video 3, we will move on to some data preparation notebooks and training our first forecasting model using Auto Urbima.
All right. Yeah. Sorry for the background noise, but yeah, this is the second video. Feel free to put any question you have in the Zoom chat. And yeah. So should we go ahead to play the next one that introduced Auto Urbima model?
Sure. Yeah. I don't see any questions. Well, I see questions around the CSV files. Yeah, so maybe I'll answer that first. Yeah.
Sure.
So basically, the question is if anyone else is having issues with the data, the CSV file is not present. So we are, somebody pastes the link to the resources again. Okay. So regarding the data is actually being downloaded as a part of the notebook. Let me see if I can share the screen just briefly to point you to that. So basically, if you look at the here data exploration notebook, the data is actually being downloaded here. So the utility function download OJ data is provided, which basically loads the data from an R package base M, which contains the OJ data. So when you run this cell, you locally after you've set up the environment, it should download the data to the specified directory here. So we don't provide the CSV
Vanja,
file.
We cannot see your screen. Can you share it again?
Oh, got it. Okay. Right here. Yeah, so basically we provide this utility function here, download OJ data as a part of our utility library here. And so after you've set up your forecasting environment following the instructions, that library should be installed in this forecasting env, so that after you execute this particular cell, the data will be downloaded in the OJ data directory here. So we don't provide the CSV files directly, but we as a part of the notebooks, we download it from the original source, which is the base M package in R. Let me see if I can see those other questions. Apologies for not being very well versed at Zoom. Let me see. Yeah, right here. Can somebody paste a link to the resources again? The link in the PDF seems broken. All right, so this is the link to the. Actually, I'll link it here. Click it here. So this is the link to the tutorial GitHub page. From here, if you actually click on this view on GitHub, it'll lead you to the actual repository on GitHub. And so all of the examples that we're going through are here. The first thing, we've kind of presented this already, but the first thing to do is to run through the technical setup. We've provided some utility scripts to do that, such as this environment setup script for Linux and for Windows. So this will install those forecasting utilities, but also all the other dependencies that are required for the examples. So once you've done that, then all of the notebooks that we're going over are in this examples directory, in this grocery sales subdirectory, which basically runs the forecasting for that orange juice data set. And as we mentioned, we have some implementations in R and some implementations in Python here. All right. Let me see if there's more questions here. All right, so there was one question on availability of ETS. We haven't implemented ETS in Python or ETS example in Python, but it's available in our examples. So if you go follow this examples links here to our subdirectory, there is sort of a bit of an explanation of what's contained here, but the ETS implementation is in this basic models RMD R Markdown file. Towards the bottom of it, there is the implementation of ETS on orange juice dataset. All right, there doesn't seem to be any more questions here, but feel free to post them as we go. So Chenhui, I'll let you share again, just so we can avoid those technical issues.
Yeah, sounds great.
And I would suggest we give, maybe after the third video, we have a break of 5 to 10 minutes, and then resume after that, just to give everyone a break.
Yep, sounds great. Okay, so up next, I will be playing the third video introducing the auto arena. Go from the beginning.
Hello, everyone. This is video 3 of our tutorial building forecasting solutions using open source and Azure machine learning. So in this video, we'll go through 2 main topics here. We'll run through notebooks that demonstrate how to prepare the data for time series forecasting, as well as how to do time series cross-validation. And in the second part of this video, we'll train a forecasting model using AutoArima, in which we'll also cover how to do forecasting evaluation. So let's jump to the notebooks. As we mentioned in the previous video, you've cloned the repository and you've started the Jupyter server. You've set up your environment. So to open these examples, simply navigate to examples directory, grocery sales, Python, and you'll get to 4 directories here. So in the quick start directories, there are a couple of notebooks here, and we'll more specifically look into the AutoArima example here. And in the second directory here, prepare data, we will more specifically look into the OJ data preparation notebook. So I already have these 2 notebooks open. The modeling directory here contains similar material as in the quick start notebooks, except that in these time series forecasting notebooks here, we're using something called multi-round data preparation and validation, which basically means similar to K-cross validation in general machine learning, where we evaluate the time series forecasting on several rounds of training and testing data. So let's go first through the data preparation notebook for time series forecasting. So this notebook introduces you on how to split the orange juice dataset into training sets and test sets for training and evaluating different retail sales forecasting methods. We use backtesting, a method that tests a predictive model on historical data to evaluate the forecasting methods. Other than standard k-fold cross-validation, which randomly splits data into k-folds, in time series forecasting, we split the data so that any of the timestamps in the training set is no later than any of the timestamps in the test set to ensure that no future information is used. This is an exclusion with certain information that actually may be available and known beforehand. So, for example, price of the product in the next few weeks is usually set in the future, so that we can access this information when we do the forecasting. All right, so in the first couple of cells, we are basically importing the libraries required for this notebook and telling the notebook here to download the data. We've gone over the description of the dataset in the previous video, so we can skip this section. Here we will showcase two scenarios, splitting the time series dataset into a single round and splitting the time series dataset into multiple rounds of training and testing data. So we've created a utility function called split train test, which uses several parameters here to split the time series into training and testing data. So let's describe these parameters. Number of splits defines the number of training and testing splits we want to split our data into. The horizon, or the forecasting horizon, determines the number of weeks to forecast in the future, or the test period length. Gap defines the gap in weeks here between the training and the test data. This is especially relevant in retail scenarios to allow business managers to plan for the forecasting demand in the future, and to give them a couple of weeks to adjust the inventory based on that forecasting demand. First week here is the first available week in the data, and last week is the last week available in the data. So here we're saying let's split the data into one split. Horizon, or forecasting horizon, is 2 weeks. Gap to leave between training and testing data is 2 weeks. First week available in the data is 40, and the last week available in the data is 156. So the split train test function will split, based on the above parameters, we'll split our data into what looks like the following chart. So our original time series is available from week 40 to week 156. We have one round of splits, so one training data set and one testing data set. We have 2 weeks, the forecasting horizon to forecast into the future. We have 2 weeks between training and testing data, so that our training data ends in week 153, and our testing data starts in week 155. So to actually split the data into the single round forecasting, we simply run the split train test function based on the parameters that we've set above. So now if we peek into the training data here, we'll see that our training data begins in week 40, and our testing data here starts in week 155 for each store and brand in our dataset. Auxiliary dataset here is extracted just basically to contain all of the other external features in our data, whereas the training and test really focuses on the log move column here. But it's not relevant at this point. We're just demonstrating how to split training and testing data. So to do the multi-round forecasting, or multi-round splitting here, we can set the parameters and splits, or the number of splits, to 5. So if we've set this parameter to 5, the forecasting period that we generate in each test rounds are non-overlapping. So this allows us to evaluate the forecasting model on multiple rounds of data and get a more robust estimate of our model's performance. Non-overlapping, what that means is that basically our testing periods that we're evaluating on are non-overlapping in time. So that in first round, our training data goes from week 40 to 145, and our testing data goes from 147 to 148. In the second round, our training goes from 40 to 147, and our testing data goes from 149 to week 150. So that we can see that the weeks that we generate in multi-round splitting here are all basically non-overlapping. And so that our last round, or round 5, will look like the single split here in the single split scenario, where our training data goes from week 40 to 153, leaving a gap of 2 weeks before training and testing, and forecasting 2 weeks in the future, week 155 and week 156. The parameters that we've passed basically specified what this multi-round forecasting will look like. So again, to split training and testing, we use split train test function with the updated number of splits of 10. So in actual modeling notebooks that we'll run later, we'll use number of splits equal to 10, simply to increase the number of evaluation period and to get a better estimate of model performance. So what our data will ultimately look like is, this is the first split, this is the training weeks in the first split, the testing weeks in the first split, and so on, up until the last split, where we have the training data from week 40 to week 153, and the testing data week 155 to 156. So this for loop will ultimately generate all of those rounds of splits. And so this is basically just printing out some information for each round. And we go again from round 1 to round 10. So this is just a notebook to demonstrate on how to split time series data and prepare it for forecasting model training and forecasting evaluation. So once we have our data split, let's look at running AutoArima on our data here. So this notebook, again, I'll navigate back to where we found this notebook. So this notebook will be in the quick start here, and it'll be titled AutoArima single round. So this notebook provides an example of how to train an ARIMA model to generate point forecasts of product sales in retail. We train ARIMA-based model on the orange juice dataset again. So an ARIMA, which stands for Autoregressive Integrated Moving Average Model, can be created using an ARIMA PDQ model with Stats Models library. So in this notebook, we will be using an alternative library, PMD ARIMA, which allows us to automatically search for optimal ARIMA parameters within a specified range. More specifically, we will be using AutoArima function within PMD ARIMA to automatically discover the optimal parameters for an ARIMA model. This function ultimately wraps ARIMA and seasonal ARIMA models of Stats Models library, which corresponds to non-seasonal and seasonal model space respectively. In an ARIMA model, there are 3 parameters that are used to help model the major aspects of time series: seasonality, trend, and noise. These parameters, as I mentioned above, are P, D, and Q. P is the parameter associated with the autoregressive aspect of the model, which incorporates past values. D is the parameter associated with the integrated part of the model, which affects the amount of differencing to apply to a time series to make it stationary. And Q is the parameter associated with the moving average part of the model. If our data has a seasonal component, we use a seasonal ARIMA model, or ARIMA, small PDQ, capital PDQ, M, in which case we have an additional set of parameters, capital P, D, and Q, which describe the autoregressive, differencing, and moving average terms for the seasonal part of the ARIMA model. And M parameter refers to the number of periods in each season. All right, so after importing the libraries that we'll need in this notebook, we look at our parameters here. Since we will be using AutoArima function, we will ultimately let the function itself pick the optimal PD and Q parameters for our data. AutoArima function does take as input a range, so it does allow us to specify minimum and maximum values for these parameters, simply to narrow down the range, the search space that it needs to search over to find the optimal parameters. So this is something that you should pay attention to, because if you specify too narrow of a range, then AutoArima may miss out on the optimal parameters for your data. However, if you specify too large of a range, then training a model may take a really long time, as AutoArima searches over a really large space of parameters. So we note in our data that our data does not show a strong seasonal component. So we will not be searching over the seasonal ARIMA models. We're narrowing down the search over non-seasonal ARIMA model. And if you wanted to change this behavior and search over the seasonal models, simply set this seasonal parameter here to true and include the start capital P, start Q, start capital Q, start max capital P, and max capital Q parameters in auto ARIMA function. Excuse me. Think. So now we kind of demonstrated here where you can play with the parameters of auto ARIMA model training, and we move on to the data preparation part of the notebook. This is again where we use the split train test functionality of FC library provided in this repository, where we split the training or split the data into training and testing. So when running this next cell, would achieve that task of splitting the data into training and testing. Our time series data is not complete since we have missing sales for some stores and products in particular weeks. So we will fill in those missing values by propagating the last valid observation forward to next available value. We will define functions for data frame processing, then use these functions later within a loop that loops over each forecasting round. So note that our time series are grouped by store and brand, while week represents a timestamp and log move represents the value to predict. So let's first process the data. So if we execute this cell, it will select only the columns that we want to use in forecasting here. Notice that the unit sales of the products are given in logarithmic scale, so we will use this quantity for training the forecasting model as it smooths out the time series and results in better forecasting performance. We will later convert the log move to a unit scale for evaluation for consistency across all of our examples. So if you look at the processing the data here to fill in the missing values, when we peek into the training field data frame here, we basically get a value for each store, brand, and week. We do the same here for processing the test data to obtain the test field data frame. So we next train an ARIMA model for a single time series, simply for demonstration. So let's select store 2 and brand 6 and filter our data based on these values. So for store equals 2 and brand equals 6, we filter the training field data to obtain train TS or train time series, for which we'll be using in this example. So to train a model, we simply specify the auto ARIMA with the parameters that we specified at the top of this notebook, and we run model.fit. So let's look at the model summary. As seen from the summary, the selected ARIMA model is P equals 1 and D and Q equal 2. So this is a relatively simple model, also referred to as first order autoregressive model. It indicates that the time series is stationary and can be predicted as a multiple of its own previous value plus a constant. Essentially, this is an ARIMA 100 plus constant model. This is where these parameters are shown once we print out the model summary. So the model summary contains a lot of information. The coefficient table in the middle provides the estimates for the weights of the respective P and Q terms. Notice that the coefficient of the ARIMA 1 term has a low p-value here, indicating that this term is significant. It also shows that the constant term is significant with a low p-value. Next, let's examine the diagnostic plot for the selected model. In the top left, the residual errors fluctuate around a mean of 0 and have a uniform variance, which may indicate that there's no bias in prediction. The density plot in the top right suggests normal distribution here with 0 mean. The ACF plot in the lower right shows the residual errors are not autocorrelated. Any detected autocorrelation in this plot suggests that there may be some pattern in the residual errors which are not explained in the model, so adding additional predictions to the model may be beneficial. And finally, in the bottom left, we do not see significant deviation of residuals from the red line, which indicates that the model is a good fit. Overall, based on the above, it seems that the model is a good fit for this particular time series. It is worth noting at this point that selecting the best parameters for an ARIMA model can be challenging and somewhat subjective and time-intensive. Should be done following a thorough data examination, such as looking at seasonality, trend, and bias. We use an auto-ARIMA function here to search a provided space of parameters for the best model, mostly to demonstrate its usage and functionality. And given that we have 900 plus time series, selecting a single auto-ARIMA model for each time series manually can be time consuming. So let's now look at the predictions. Since auto-ARIMA model makes consecutive forecasts from the last time point, we want to forecast the next n periods points so that we can account for the gap as described in the data setup. So to predict the next points, we simply run model predict and provide it the n periods. What we obtain here is the predictions for our store 2 and brand 6 for weeks 137, 138. To evaluate the model, we will use mean absolute percentage error on MAPE. In this data frame here, we combine the predictions with the actual, and to compute the MAPE, we simply run the MAPE function that's a part of the FCLib here, imported earlier in the notebook. So obtained MAPE for this forecast is 69.4%. So to train, so next we'll train a model for across all of the stores and brands. We will basically rerun the same code to automatically search for the best parameters, as simply wrapped in a for loop, iterating over stores and brands. We will be using Ray here to distribute the computation to the cores available on your machine if Ray is installed. Otherwise, we will train the models for different stores and brands sequentially. At the time of developing this notebook, Ray only supports Linux and Mac OS. Thus, sequential training will be used on Windows. So in the cell below, we'll basically demonstrate on how to use Ray to distribute the computation on the cores. We wrap our model training per store and brand in a function here. And we are testing here if module Ray exists, then we're saying Ray is available and parallel training can start. Otherwise, if module Ray does not exist, then ultimately loop over each store and brand and train the model for each particular store and brand. Finally, once we have the model, we can look at MAPE across all of our results. Note that in the above loops that iterate over store and brand, we have collected the results into the result data frame here. And finally, the obtained MAPE metric here is 69.7%. So when building a model with auto-ARIMA for a large number of time series, it is often difficult to examine each model individually in a similar way we did for the single time series above. As auto-ARIMA searches a restricted space of the models defined by the range of P and Q parameters, we often might not find an optimal model for each time series. So let's plot a few examples and we'll see what the performance is like. So if we plot just a subset of time series here denoted by a specific store here and brand, we'll see that in some cases we obtained a pretty good prediction given in a red line versus an actual given in the blue line here. Whereas in some cases the prediction is really kind of off and more modeled basically based on the previous values seen before this gap or at the end of the training data here. And so, for example, this is a pretty good prediction versus some other examples like this one versus this one. The prediction is not so good. But since we're, again, running auto ARIMA and searching over a restricted space of parameters for each of 913 time series, it is kind of hard to visually always look into specific time series model and specific time series model performance. So we'll often find it challenging to really generalize these models across a large number of time series. For more information on auto ARIMA in general, you can refer to some of these additional reading references we've provided below. So this is the end of the auto ARIMA single round notebook. I will point you to another notebook that goes over auto ARIMA example, which is in model directory here. So as I mentioned, model directory here provides a more sort of proper setup to training and evaluating forecasting models versus what we refer to as a quick start, which basically only goes over a single round of forecast. In the modeling directory, we actually split the data into 10 rounds of training and testing splits and train a specific model, in this case auto ARIMA, dilated CNN, and light GPM, across all of those rounds and across all of the stores and brands. So if we open this auto ARIMA multi-round notebook, we will see that most of the notebook actually contains similar information as in the single round notebook. So looking at the data, how to split it, how to describe the parameters that we're searching over. But we ultimately split the data into 10 rounds. So this is just pictured here for 5 rounds for the ease of visualization, but we're actually splitting the data into 10 rounds. Let me see if this is parameter. Oh no, actually we're splitting the data here in 5 rounds, excuse me. And so when we use the same approach of using RAID to train auto ARIMA model across all of the brands and stores across each of these rounds. But ultimately we evaluate
Chenhui, hi. It seems like there's some connection issues.
All of the rounds here separately and in aggregate. So we can see that for some rounds the MAPE is lower. For some rounds it's more challenging, but the overall MAPE that we obtained on all of the rounds and stores and brands is 68.3%. When we visualize the data, again, the predictions and the actuals across a subset of time series, we'll again see the performance is not as great. For example, auto ARIMA often tends to kind of predict kind of similar value based on the last observed time series in the time point value in the training data. This is likely because a very simple model is picked as an optimal model for this particular time series. And so this is simply for demonstration purposes on this data set. For a more involved kind of time series forecasting using auto ARIMA, it may be beneficial to include some external values, external data that may be beneficial to the forecasting. In this particular example, we've only used the historical values for each time series. So this is the end of our auto ARIMA notebooks. In the next videos, video 4, we will be covering a machine learning-based approach to forecasting, which converts the time series into a tabular data set, and then runs a light GPN model on that data set to produce the forecast. Thanks.
All right. Yeah, this is the end of the video about auto ARIMA. So feel free to put any question you have. And as Vanja suggested, maybe we can have a short break after this video and then come back for the next part of the session.
Sounds good, Chenhui. So I see now it's the clock is at 16 minutes, 17 minutes. Maybe we could come back at 20 minutes mark. Does that sound good? A few minutes break.
Yeah, sounds great.
All right, thanks. All right, so hopefully everyone had a couple of minutes for a quick break. So there was one question regarding the previous example that I'll answer now before we move on to the next video, which Chenhui will present on light GBM. So basically, the question is, could you please elaborate on how you use different splits in training? All right, so I'm going to share my screen quick for this. All right, so here, let me find data preparation notebook here. So basically, we start from the entire time series, which we have week 40 through to week 156 available data for. So if we specify that we want to utilize 5 splits, then this sort of schematic shows how we split the data. So we basically, let's start from round 5 because it kind of makes more sense. So in the round 5, we, using the parameters that we specified for the splitting functions, we take the last, so our horizon is 2, which means we want to predict 2 data points or 2 weeks in the future. So we take the 2 weeks in the future as the testing data, and the remaining available data we take as training. You'll notice that we also leave here two weeks gap. This is also a parameter that we specify in the split train test function. Let me see if I can find it back here. Yes, these are the parameters. The reason we leave this gap, oftentimes this gap doesn't exist. So basically, in that case, you would take this data for training, and then everything from the week 154 backwards you would take for training. But the reason we leave it here for as a gap is oftentimes in retail scenarios, the business sales folks who are planning the inventory and so on would like to have this gap so they could so any changes that they make to their inventory can be accounted for. Let me see if there's any questions. I see some things. Okay, no. So basically, we have the 2-week horizon, we have the 2-week gap, and so everything before then is then taken as a training data. So then, in order to avoid here overlaps, we move in the next round. We take weeks 153 and 154 for testing, and again 2-week gap, and then the remaining data for training. And so on, we kind of move backwards until we've reached 5 rounds of data. So when we train our model, or when we train and evaluate our model, we would first train on the round 1 and evaluate the performance on these 2 data points. Then we train the model on the entire round 2 training data and evaluate performance on the round 2 testing data. And so on until we reach the last round. And so we train the data on the entire round 5 training data up to week 153 and evaluate on these 2 data points. This would basically give us a better estimate of the model's performance since we've seen sort of more, more splits of data. And so rather than, let's say, evaluating on only this one kind of sample points, we're hoping that, these testing rounds here would give us a bit more diversity in terms of the data and therefore test the model more rigorously. Hope this answers your question. Let me see if there's anything else. All right, so no more questions. Chenhui, if you'd like, you can move on to the next video.
Okay, sounds great. So up next, I'll be playing a video introducing the light GBM example.
Hi, Chenhui. You're not sharing your screen. I don't know if you're having some issues.
Sorry.
Mm-hmm.
Yeah, sorry. Yeah, I may have forgot that. So let me share my screen again. I thought I did share. All right, so maybe I will so start from here. So can you see my screen now?
Yes. Mm-hmm.
Okay, great. Thanks for that. Sure.
And GPU learning, as well as the capability of handling large-scale data. Due to these advantages, it has been widely used in solving various machine learning problems. To run the LightGBM example, we first need to activate the forecasting env conduct environment. Then we can launch the notebook using Jupyter Notebook command. Here I'm launching the notebook from a remote VM. That means I also need to forward the port 8888 to my local machine. I have already done that. So that means I can directly copy this link and then open up the Jupyter Notebook on my local browser. So this is the root directory of the forecasting repository. If you click Examples, Grocery Sales, Python, and then go to Quick Start, you will see the LightGBM single round notebook. In this notebook, we first import LightGBM, forecasting lib, and other necessary components. So let's run through the first two cells. As you can see here, you can find out the system version as well as the LightGBM version. And then we set the global parameters, which include data directory, forecasting settings, parameters of the LightGBM model, and the parameters of feature engineering. Next, as in other example notebooks, we download and split orange juice dataset into training and test sets. The data contains weekly sales of orange juice and other related information, such as price and promotion. Okay, after that, we're going to generate features for training and forecasting. Specifically, we use date time features, including week of the month, and month. Also, we include historical weekly sales of each orange juice brand in recent weeks. In addition, we compute average sales of each orange juice during recent periods and include other features like store, brand, deal, advertisement, and price information. Using the utility functions in FCD, we can create each of the above features and combine them into a data frame. As we can see in the printout message of this cell, after we run the cell, the feature data frame includes 29 columns. So let's run this cell. It will take some time.
Yeah, so by the way, I was running this example in a very small VM, so it's a little bit slow.
So this is the feature data frame. Once we have the features in place, we are ready to train the LightGBM model and use the trained model to generate forecasts. Here, we just train a single LightGBM model for predicting the weekly sales of all the stores and brands. This allows the model to learn common patterns across different stores and brands. It also makes the model training much faster compared with training separate model for the combination of each store and brand. So the model training will take a couple of minutes. So let's just be patient. If you would like, you can also grab a cup of coffee and then come back to check the results.
So I just want to add a quick comment here. So this the training speed is highly dependent on the hardware device, namely the GPU or CPU that you are using. So I was using a very basic VM, which has probably only 2 cores and also small memory size on the computer. And I can probably just speed up this process, and then later I can quickly showcase how much time it will take to train the same model on my laptop, which is actually much faster. It's about maybe 2 or 3 minutes, or even quicker. So let me just quickly go to the end of this model training process, because this is actually much slower than I was expecting.
Model training and prediction just finished. Next, we can evaluate the model performance by computing MAPE on the test set. We can see that the MAPE is about 35.6%, which shows that the model does a pretty good job. We can also check the feature importance that the model has learned. This chart shows the top 20 features that are most important for predicting the sales. We can see the store brand price ratio as well as a number of lagged features are of great importance. Lastly, we can further visualize the forecasts against the actual sales using a convenience function in FClib. Here we plot the results of 6 sample stores. From these plots, we can get a closer look at the prediction. Okay, that's all about the light GBM example. Hope you will find it helpful. In the next video, I will further introduce how to tune hyperparameters of light GBM model using hyperdrive in Azure Machine Learning.
All right, so this is the end of this video. So again, yeah, please feel free to raise any question. And also, since we have some time, so I would like to quickly showcase how you could run the example, say from your local laptop. Here, so I have already cloned the repo, and then I simply just also I prepare the environment. So you can see I have this forecast env environment. So then I just activate this environment and then run Jupyter Notebook from this environment by simply using this command Jupyter Notebook. And then you will see that I can open up the repo and find the example that I want to run. So here I'm interested in this light GBM example, for example. So then see. Open the example. Maybe I can reopen it. Just try to see if this works or not. All right, yeah, it seems this this color has died. So let me just quickly close it. Yeah, and then
Chenhui, your voice is a bit faint, so if you could just speak closer to the microphone.
Okay, so I just restarted, and then I will go to the quick start example of LightGBM again. See if I can open. Sometimes your computer may not cooperate with you. Okay, now it works. So after you open the example, so since I already walked through the details, so quickly I can just, if you would like, you can click run. So you could actually use run all. You will simply try to run the entire notebook, and then you can just like monitor what happens in the web browser here. Yeah. So here, yeah, it tries to actually download the data, but data is pre-existing, so data download step is skipped, but still it needs to split the data into multiple training and testing runs. So that's why it still like takes some time. Here in this cell, it is trying to create all the features that I need. For example, date time features, price information, and advertisement information, and elect features and the rolling features. And then later, all the features will be combined into a single data frame. Yeah, and also during the process of like creating the rolling features, elect features, you will see some missing values in the beginning of the or in the first few weeks for each brand. So that's why it is reporting some of the missing rows. Then all these missing rows can be simply removed. And then now we are entering the model training process. Here, it seems much faster than I was observing on the VM. Yeah, and then you can, if you take a close look, you can see the training map is keep increasing. And to be honest, if we compare this with like, for example, Auto Arena, even the first round training map is much smaller than the map that is on the Auto Arena, meaning that LightGBM model can actually capture a lot of variance in the data. But we do need to be very careful to avoid like train or overfitted LightGBM model, because you can see the map can keep decreasing to very low number. So that's why we actually put an early stop criteria, as well as like limited the number of iterations to 940. So these hyperparameters are actually tuned using hyperdrive, which will be the hyperparameter tuning process will be introduced later in another video. Okay, so yeah, after model training finished, we got the same result as what we saw previously. And then again, yeah, we can plot the forecasted results. All right, yeah, this is the LightGBM model. There is another LightGBM model example. Okay, go back here. Yeah, there's another LightGBM example in model folder, which actually does multi-round training and testing using LightGBM. Maybe I can just quickly open up this notebook and then show what we have here. So essentially, in the beginning, we are doing similar things like loading all the necessary components and then specify hyperparameters. we will be talking about hyperparameter tuning later to see how we write this set of hyperparameters. And then similarly, we do data preparation, feature engineering. Here, since we need to prepare features for multi-round training, so we actually wrapped up the whole procedure into a function called create features. And then you can just specify which round you are at, and it will create the features as a data frame for your current round. And similar to the auto RIMA example, you can see we do data split in a similar fashion. And then we can just simply do multi-round model training. So in each round, we use the historical data we have to train the model, and then generate forecasts for 2 weeks in the future. Okay, and then eventually we can combine all the forecasts in a single data frame, and then we can evaluate the prediction made for all the forecasts that we have generated. So the MAPE is slightly less than 36%. So it's actually a very good result, given that we have very fluctuated data. So again, we can see the forecasts in this sample plots. So in this one, we can see like there are like 2 or 3 spikes we didn't capture using the model. But in this one, it seems that we can we can capture all the spikes fairly well, except the last 1 or 2. And then also similar to this one. It seems that yeah, the LightGBM model overall can capture a lot of variance or spikes embedded in the sales data. That means probably 2 things. Like first, by incorporating more features, we can explain more data variance. And also the second is LightGBM model has very strong capability of learning those patterns from the data. Yeah, that's pretty much all about the LightGBM example. Yeah, so feel free to let me know if you have any questions. I'm not, again, very good at showing video. Okay. So yeah, it seems that we got a bunch of questions. So let me try to answer some of them at least. So this one from Moon. So do you perform sensitive analysis during forecasting? Oh yeah, so yeah, Vanja has already replied. Yeah, so overall, I think yeah, we haven't done like any like sensitivity analysis at the moment, but we do like split the data into multiple rounds to evaluate the stability of our model. But depending on what kind of sensitivity you are looking at, for example, you may wonder if your data is a little bit perturbed and how your forecast will be changed, will be altered accordingly. So you could actually add some permutation or noise to your training data. But overall, this is actually a very interesting question, and yeah, feel free to put additional details to explain to explain your question in more details. And also, so another question is about, is multi-round model just equivalent to a model which is validated in k-folds? I would say it is very similar, except that when we split the data. We don't like randomly commute all the data points and then pick like a certain portion as training data. We use a moving window to keep increasing the length of training data, and then keep forecasting the sales in the next 2 or 3 weeks, depending on your horizon. So that's pretty much what multi-round training does. And yeah, and also the multi-round training is also mimicking the scenario in practice where you will have like a data point of your sales coming in like probably every week, and then you want probably retrain your model also regularly, like every 2 weeks or every month. So this is essentially mimicking the same like scenario that you would have in practice. Okay. Let's see if there's any more question. Yeah, the training maybe is about 0.2, but the prediction is about 35. Is that overfitting? Yeah, that's a really good question. So if we define like overfitting as like a training, sorry, the training mate is less than the testing mate, then I will say this is overfitting. But very interestingly, we observed that by allowing some degree of overfitting, we actually also boosted the performance on the testing set. So, but here a disclaimer is that when we do model training, we actually or hyperparameter tuning, we haven't looked at any testing data. So we simply all the hyperparameters we use here is simply discovered by hyperparameter tuning notebook, which further splits the training data into a subset of training and a subset of validation, and then do hyperparameter tuning. After this, we find out this set of hyperparameters. So these set of hyperparameters actually tend to make the model a bit overfitted. That's what we observed. Depending on how you actually pick the hyperparameters, maybe if you, for example, when you split the training data into a subset of training and validation, the portion of the validation set, and also how you split the data, either split the data randomly or like or like split the data by using like data older than a certain time point, or data is after a certain time point. So these kind of criteria that you use in the hyperparameter tuning may impact what hyperparameters you got. So yeah, we will see more details about the hyperparameter tuning. But so in a nutshell, so what we observed here is that the hyperparameters that we found by doing hyperparameter tuning actually does make the model a bit overfitted. And it's still kind of open question to see if we kind of like pick another or like make some changes in the hyperparameter tuning process, and then we may or may not see a very different model, or like simply we may or may not like resolve this kind of overfitting issue, or maybe this is simply not a very big issue in practice, because like you will see like the end goal is actually to check the test accuracy. As long as the test accuracy is decreasing, I think yeah, you are moving towards the right direction. All right, let's see if there are more questions. So another question is, for each round in multi-round, do you train each model from scratch? Okay, this is another great question. So for light GBM model, it does model training in every round using all the historical data. But for another model, the dilated CNN model, we actually only retrain the model using a small portion of the latest data points. We do this because of like two reasons. First, we want to speed up the model training process for dilated CNN. And secondly, we also want to see how model retraining using like only the latest data points perform compared with like simply training the model using all the historical data again in the next round. Yeah, here, let me double check. Yeah, I think, yes, that's true. So we actually did model training in every round using all the historical data for light GBM. Okay, and so how did you choose the hyperparameter research or experience? Yeah, this is what we will cover in the next video. We use hyperdrive from Azure machine learning to tune the hyperparameters in a distributed manner. The algorithm we use is a Bayesian sampling strategy, which actually turns out very effective. And because of the hyperdrive distributed computation, the hyperparameter tuning process can be carried out very efficiently. Okay, so if there's no more questions, then maybe we can move on to the next video. Yeah, and again, feel free to add more questions while I'm playing the next video. Okay, so the next video will be introducing hyperparameter tuning.
In this video, I will walk through how to perform hyperparameter tuning using hyperdrive in Azure ML to improve the accuracy of the forecasting model. To find this example, you can go to GitHub repository and navigate to the table of content. By clicking this link, you will see the...
I don't hear the audio from the video. Maybe let me reshare my screen. Sorry about that. I'm not sure what's wrong.
In this video, I will walk through how to perform hyperparameter tuning using hyperdrive in Azure ML to improve to the table of content. After that, we initialize a Azure ML workspace. As you can see, this script runs properly on the local machine as it returns the map on the validation
Hi,
set.
Chenhui. We can hear your audio clearly, but we cannot hear your own voice. Your own voice is kind of low.
Oh, sorry.
Yeah, yes, the video is coming through pretty well. Your voice is kind of faint, yeah.
Oh, sorry. I think I accidentally hit a button. I mean, my audio was shut off, so I cannot hear myself. So let me just play this video again. Sorry for the inconvenience.
In this video, I will walk through how to perform hyperparameter tuning using hyperdrive in Azure ML to improve the accuracy of the forecasting model. To find this example, you can go to GitHub repository and navigate to the table of content. By clicking this link, you will see the example notebook that shows how to tune hyperparameter of the LightGBM model and deploy the best model as a web service. In the beginning of this notebook, we set up Azure ML widgets that help monitor the status of job running on Azure ML. Then we import necessary components from Azure ML SDK, fclib, and so on. After that, we initialize a Azure ML workspace and create an experiment. We also need to download the orange juice dataset and split it into training and test sets. To tune the hyperparameters, we have prepared a model training and validation script. This script takes a set of input hyperparameters and train LightGBM model with these hyperparameters. Then it measures the map of the model on a validation set. Before we run this script on Azure ML, a good practice is to test it locally. As you can see, this script runs properly on the local machine as it returns the map on the validation set. Next, we will also test this script on a remote compute. To do this, we first create a CPU cluster as the compute target. Then we also need to configure a Docker environment using the convenience functions provided by Azure ML SDK. In addition, we upload data to default data store associated with Azure ML Workspace. Finally, we can create an estimator to define the job and submit the job to the remote compute. We can check the job status using the runDetailed method. Now, we will use hyperdrive to tune the hyperparameters of LightGBM. Here, we define the hyperparameter space and the hyperdrive job configuration to specify the hyperparameter searching job. We are going to tune 9 hyperparameters jointly using Bayesian sampling method, which is an intelligent random search algorithm. Although our hyperparameter space is very big, with Bayesian sampling, we can quickly find a model with great performance after just 20 trials. Here we specify the number of trials in the parameter max total runs, and define the maximum number of concurrent jobs in the parameter max concurrent runs. From the information retrieved after the searching job is done, we can see the validation map of the best model is around just 30%. Which is a very good number. Lastly, we can also deploy the best model as a web service running in Azure Container Instance. To do this, we prepare a model script. We prepare a model scoring script that loads the model and scores it with the test data. Then, we create a conda.yaml file to specify the dependencies. After that, we can deploy the model as a web service in less than 3 minutes. After the model is deployed, we can test out the web service by sending an HTTP request to the service. And then we can also check the forecasts that the web service returns. After you have tested the web service, you can also delete the web service. That's all about this example. In the next video, I will introduce how to build dilated CNN model for demand forecasting. Thank you.
All right, so this is the end of the 5th video. And I will quickly check if we have more questions. Seems like the chat is not working for me right now.
Hi, Chenhui. There's one question here from Jeremy, if you want to read it and answer.
Okay, yeah.
And your voice is still a bit faint, if you could speak closer to the microphone.
Okay, sounds good. So interestingly, I couldn't like click the chat button to see the question. Could you mind,
Sure.
like,
Yeah, I can read it. The question is, can you talk a little about the setup here? I'm assuming this must be run on an Azure ML session.
Yeah, yeah, this is a great question. So let me go to the repo to share more details. So here, so for example, if you go to, again, the example, it has actually a lot of details about how you should prepare the environment. So let me maybe just spend a couple minutes just highlight what kind of preparation steps you need to perform. So first of all, we use hyperdrive in Azure machine learning. So you need to first get an Azure machine learning account. I suggest that maybe you can get a free trial account first to kind of get a flavor. And then let's see, once you have the Azure ML account, I think additional thing you need to do is to actually install some of the dependencies. But actually, so the dependencies include like Azure ML, this package, Azure ML Python SDK, as well as like these Azure ML widgets for visualizing some of the model training process in Jupyter Notebook. So I think these two are the main dependencies. And for Azure ML, you don't need to worry as long as you can go through the setup script that we shared in the beginning of the tutorial. It will include or install Azure ML package in the forecasting ENV Conda environment for you. So what you need to do is simply make sure you start or launch this notebook from the Conda environment that is created by the setup script. And then this part is what you need to run like before, like really running your like script using hyperdrive. But other than that, I think you are good to go. Yeah. Oh, yeah. So there are a bit more details that you need to you need to know. So after you created an Azure ML account, you can further initialize Azure ML workspace, and then create an Azure ML experiment. So I think one thing you need to do manually is to create this Azure ML workspace. You can do this either in Azure portal in the portal.azure.com, or like you can create or initialize the machine learning workspace using Azure CLI, and eventually you can you can find out the subscription ID, resource group, workspace name, and workspace region after you created the Azure ML workspace in the Azure portal. And then you just need to replace the corresponding information that you have replace these placeholders by using your own information. And then you should be able to run through the entire notebook here. Yeah. So I'm not sure if this helps. Please feel free to let us know if you have further questions.
Yep, Jeremy said, very helpful, thank you.
Okay, yeah, you're welcome. All right, so so we have another video, which is the last video about a deep learning model. So I will play this video, and then hopefully we can have more discussions later.
In this video, I will go through the implementation of a dilated CNN model for demand forecasting. In the GitHub page, if you click the URL of dilated CNN in the table of content, you will open up the Jupyter notebook of this example. Dilated convolutional neural network, or dilated CNN, is built on dilated causal convolution. Recent study shows that it outperforms recurrent neural networks such as LSTMs over a diverse range of tasks and datasets. Dilated CNN has many advantages when handling sequential data like time series. First, it can capture long-range input information with less parameters. Second, it handles temporal flow with causal connection structures. In addition, it has better training efficiency than recurrent neural networks. In this notebook, as usual, we first import all the necessary components. Here we mainly import components from TensorFlow and FClib. Then we specify global parameters of the experiment. These parameters include data directories, forecasting settings, model parameters, and feature columns. In addition, to increase the reproducibility of the results, we fix the random seeds in the Python modules. Next, we download the orange juice data and split it into multiple rounds of training sets and test sets. After that, we extract a number of features from the data for training the forecasting model. These features can be divided into dynamic features and static features. The dynamic features include date-time features, historical weekly sales in recent weeks, absolute price, and the ratio between absolute price and average price of all brands, as well as promotion information. Static features contain the store ID and brand ID. Then we define the structure of the dilated CNN model and use this model to perform multi-round training and evaluation. To speed the training process, we only train the model on full training set in the first round. In the subsequent rounds, the model will be retrained using the latest data. After the model is trained in each round, it is applied to generate forecasts for the target weeks. We use a utility function called create DCNN model to define the model. After this, we can print out a summary of the model structure. To train the dilated CNN model, we also need to prepare the input and output data in the correct format by using these two data transformation functions. Then we are ready to train the model and use the trained model to make predictions. Since we have 10 rounds of model training and evaluation, this cell will take a couple of minutes to run. If you like, you can also check the model training process using TensorBoard. But this is an optional step. Finally, we can also evaluate the model performance on the test sets. As we can see here, the overall MAPE is around 37.7%. We can also visualize the prediction results against the actual cells. From the sample time series shown in the plots, we observe that the forecasts by the model are close to the truth, except if there is a very big spike in the actual cells. That's all about the dilated CNN example. Thank you very much for your attention. And this also concludes the whole tutorial. We hope the examples in the tutorial are helpful to you. In addition, this repository welcomes contributions and suggestions. If you would like to do so, please feel free to check the contribution guide. Thank you.
All right, so this is the end of the last video. Yeah, so up next, I think we have like a lot of time to take more questions.
All right, Chenhui, there's just one question here. It's from Ping, and it says, have you tried or compared profit algorithm? Is it better or worse?
Okay, yeah, this is a great question. So we actually tried profit algorithm, but we only implemented this in R because I think we want to have both like some algorithms in R and some algorithms in Python. But eventually, if we have time, we can also include profit in Python. So maybe let's see. I can quickly open up the example to give you more details. And then maybe Vanja, if you have more details that you want to provide, you can also chime in. So I will be just quickly point out where the R example that implements profit is. So if you go to grocery sales and click R folder, we have like one notebook here called profit models. So yeah, here is the profit model. And I'm not sure if you view this from the GitHub side, you will get a better view. But here you basically just see the source code, and there is also another HTML file. I think yeah, it would better like open up that from the GitHub side. For example, here we have that here. Profit HTML. Yes, yeah, this is much better. So in this example, we implemented profit in R, and you can see what's the MAPE that it produced. I think it's about it's again around 66%. If I understand correctly. Yeah. Yeah, but there could be a bit still some room to improve, I guess, by doing some hyperparameter tuning here. Here we already included like some external features, yeah, advertisement feature, price feature, and so on. But in terms of the hyperparameters, I think it could be further optimized. Vanja, do you have any additional information to add here?
No further information, just I shared a link to this example in the chat. And just to say that there's some differences in the setup of the data, some minor differences in the setup of the data between R and Python examples. So we didn't compare Python examples directly to the R examples. But the examples within each language can be compared against each other. So we're not comparing the MAPE obtained in the Python, let's say a REMA example versus the Prophet in R, just because of these minor differences in the data setup. But feel free to check out these examples and give us any feedback if you have.
Yeah, sounds good. So, any additional questions?
Yep. I would say let's stay on the line for 5-10 more minutes, or as long as there are questions or any comments. But at this point, we've kind of concluded the material for the tutorial. Feel free to get in touch with us through the repository or through our contact information and give us any feedback. Thanks everyone for attending.
Yeah, thank you everyone for your time and interest. Yeah, again, as Vanja mentioned, feel free to put additional questions or visit our GitHub repo and create like a issue there to let us hear your feedback. Thank you. Yeah, so I think Vanja and I will be here for the remaining part of the time. In case any one of you have additional questions.